Okay, today we are very happy to have Professor Ji Hui to give us the talk. Professor Ji Hui is currently an associate professor in the Department of Mathematics and the Institute of Data Science at the National University of Singapore. He is also the director of the Center for Wavelet Approximation and Information Processing at NUS. He received his PhD degree in computer science from the University of Maryland at College Park in 2006 and joined NUS after that. His research interest covers computational harmonic analysis, image processing, computer vision, and machine learning. Professor Ji will talk about self-supervised deep learning for image recovery. Hi, Ji Hui, it's your time.
Okay. Okay, thank you. Can you hear me?
Yeah.
Okay, great. Thanks for the introduction, and especially thanks for the invitation from the committee to give me opportunity to give a talk in this wonderful seminar. It's a great pleasure to share some our recent works on deep learning for image recovery. Okay. Okay, so we all see that we start with the most basic task in image recovery, image denoising, so that you're going to have a noisy image Y, which is damaged by some measurement noise. And so you want to get the true image X from a noisy measurement. This is a very basic task in image recovery, also the simplest one. Then, for instance, we can also have other inverse problem in image recovery. One typical application is image deblurring. So the problem can be formulated as a linear inverse problem, and that is if you have a blurred and a noisy image, which is actually corresponding to you running a smoothing kernel on a latent clear image and damaged by some noise. So the image deblurring is then about to deblur the image and so as to recover all image details. That's image deblurring or image deconvolution. Another one is image reconstruction in computer sensing. So in computer sensing for MR imaging, you're going to take partial measurements on the object, which can be you run some like a Gaussian random matrix to take partial measurements only. Then you want to recover the image from these partial measurements. Okay, it is air-conditioned problem. So these are typical tasks for image recovery. So actually, many of such image recovery problems can be formulated as like just solving a linear system. So you have a linear system and you have a matrix A, which is a measurement matrix, and you want to solve this matrix so as to get X from Y. And of course, for the simplest task, image denoising, A is identity. Therefore, it is not ear-posed. It's a well-conditioned problem. But in this case, usually when people talk about image denoising, they consider that the noise is severe. You have a very high level of noise, so as to the signal-noise ratio will be low. And for the image deconvolution, it is an ear-conditioned problem because the high frequencies of an image are severely attenuated when you run a low-pass filter on the target image. For the compressive sensing, because A will be a fat matrix with much more columns than the rows. As a result, you're going to have much more unknowns than the available measurements. So different problem will have different A's with different properties. Of course, okay, I'll do this. Okay, then when people to solve image recovery problem, the focus will be on two things. The first is when you solve the system, how to suppress noise magnification, because often the A can be ear conditioned or ear posed. The second is if A is ear posed so that the A is not invertible, then how to resolve the solution ambiguities, because now you're going to have a null space from A. So in last 2 decades, regularization method will be actually is a popular, very popular choice. So basic idea about regularization is that you just impose certain prior on the image. As long as this prior holds true, you get a good result. So in such a way, the problem can be formulated as optimization problem. You just have this fidelity term. Here I just assume the Gaussian white noise, and you have a regularization term psi. This psi is actually derived from the prior you imposed on the target image. So for instance, one very popular one is you model an image by a piecewise smooth function. That is, you consider this image is a piecewise smooth function. Then you're going to have a sparsity-based priors on the image gradients. That is, the most local variations are 0 or close to 0 because image is piecewise smooth. So you only have large variation along those discontinuities. So here I show you one example. You have an image F, then I just calculate the magnitude of the horizontal gradients and the vertical gradients. This partial derivative, you can see most are dark. Dark means the change is smooth, so that the local variation is close to 0. This sparsity prior actually, then people usually formulated this sparsity prior using the LP norm, either L0 norm or L1 norm. And they have, for instance, then the choice will comes to how you're going to measure these local variations. So most seminal work is total variation regularization, right? You assume the first gradients along horizontally and vertically, then you take the L1 norm of these first order gradients. This is famous total variations. You also have other generalizations like generalized total variation and others. Another one is often used, especially in our group, is wavelet regularizations. So you still have such measurement on the local variations, but you are not just using a horizontal and a vertical difference operator. You're also using the filter bank from the wavelets. Actually, this actually can somehow better model the these gradients along the different directions and the different orders. So it's just about how to design different measurement on the local variations, which give you different L1 norm relating regularizations. Okay, this is a classic. Another one very popular one, indeed, in the, I would say in the non-learning method, this non-local method often produce the state-of-the-art result. So just such approach is actually based on the so-called non-local self-similarities. Okay, so you have representative works including the non-local mean and BM3D, block matching and 3D filtering. So here I give you examples on this BM3D. BM3D just cut the image into small pieces, which means you have a large image, you cut into, for instance, 8x8 small pieces. Then you assume that each piece you can find many similar pairs. Okay, therefore then, because which means for each patch you're going to have multiple instances, right? They are same thing but with different noise independently, and then which means you just do a simple average, you can do a good things. So therefore, the basic procedure of BM3D is you just search and group similar patch together, and you process the set of such similar patches. This is the basic idea, and indeed it is very powerful. So you can look at the image in the right side. Here I show you those small patches with different color, like red box, green box, and the blue box. You can see this green box contains the same similar patches, which means you can group them together and process simultaneously. That gives you a very good prior. Okay, these are the typical traditional approach. Of course, in the last 5 years, deep learning has been a prominent tool for solving many challenging problems, including image recovery. So for the deep learning method, the basic idea is that you just train a deep neural network to learn the mapping between the degraded observation and the latent image X. And the training means just learn these network parameters. Indeed, most deep learning methods with state-of-the-art performance actually supervised. So let's consider an example for image denoising. So basically, you just want to train a network F with parameters theta. Then you are provided many pairs of noisy image and its truth image. You have such pairs. So what you did is just directly train the network, which made such that the prediction from the noise image will be as close as possible to the truth image. So that's image denoising. It's quite the paradigm is actually quite simple. For the linear inverse problem, things can be slightly more difficult because you also might just say, I do the same thing as I did for the image denoising. I just directly train the network to map the Y to the X, okay? However, you can see in this case, you don't use the model prior. That is, the matrix information of the matrix A is not used. Okay, in this case, actually, you can observe the result usually is bad. Actually, a better or more popular approach in the last 5 years is the so-called optimization unrolling. Okay, the basic approach is just follow some, you just get some iterative method from some existing regularization. Then it can be expressed as the estimation at different time, iteration 1, 2, 3, 4, and go on. Then for each iteration, you try to replace the traditional regularization step by a neural network-based mapping. So you can learn these regularizations. This is a so-called optimization unrolling. So let's take examples. So I just choose a very simple one. This one is not popular in the traditional regularization method because somehow it's slow, but it's quite popular for a deep learning method to start with. So I consider a half-quadratic splitting scheme. So because it is L1 norm regularization, right? So this is non-separable, and this is the term which causes trouble. So I introduce an auxiliary splitting variable z, so I can split. So I introduce z, which approximates this partial x. Then I regularize this z using sparsity prior. This is so-called half-quadratic splitting scheme, and you can see it can be done efficiently because each subproblem you're going to have an analytic solution. So your inversion, you get estimation, then you run some L1 norm based regularizations. This is half-quadratic splitting schemes. So if you want to, then you can, based on this, you can design a neural network so that you just replace each regularization step by a neural network with learnable parameters. Then you are done. You construct a neural network which follows this half-quadratic splitting scheme with regularization being replaced by a learnable neural network. Then you train the neural network on the training examples, you are done. Okay, actually there are many optimization unrolling methods are proposed in the past 5 years, all right? The main difference among these methods is which iteration scheme you're going to choose. Okay, and for the network, usually people prefer using CNN. I see few works on how to design neural net. Most people just either using plug and play or some trainable CNN, the convolutional neural network. Okay, so main difference among existing method on the supervised method is just about which iteration scheme you're going to based on. All right, so of course, if we think about the state-of-the-art performance of supervised learning method, the key is you have a good training data set, because this training data set means you have many pairs. Each pair contains a degraded observation and a choose image. Okay. However, in practice, you're going to have many issues on such a prerequisite, because first, collecting training samples is actually not easy, right? For instance, you want to collect a noise-free image in practice is somehow very hard. Also, collecting the training samples in medical imaging and scientific imaging can be very challenging and costly. Secondly, it's actually also very dangerous. Say you collect a training data set, then I train the network I use to do the prediction, because this one you have to assume the image you want to process will be strongly related to the training samples. If the training samples do not contain the image structures in the image you're going to process, you might introduce something artificial. This, which means you're going to introduce bias. Okay, also in existing supervised method, you got issues is that because for the different A, you have to actually carefully train each different neural network model, because usually you don't have a universal model which can handle different types of A. Even worse, for the same type of A, for instance, I consider image deconvolution, right? So you cannot train a neural network which can handle the data which is blurred by the different degrees. Usually, you have to train the network on the data which with that particular degree of particular blurring degrees, and you use it to process the data with the same blurring degrees. You actually have all kind of generalization issues for supervised one. Of course, in last I think 2 years, they have been tremendous interest on how to relax this prerequisite on the training samples for developing a deep learning based solutions. Okay, so in last 2 years, you have a very rapid progress on image denoising, so to relax the requirement on the data set. So for instance, in 2 years ago, in 2018, there is so-called noise to noise. That is, I collect 2 noise image of the same image. It's called noisy to noisy. This is called weakly supervised. Then you have the so-called unsupervised. Unsupervised usually means you have a bunch of noise images without choose. For example, you have 10,000, 1,000 noise images. Then you try to train the neural network so to do the denoise. This is unsupervised. The self-supervised usually here refers to I don't assume any training samples, not even the noisy images, except the image I want to process, which means I have zero access to any external data. So actually, there is a very interesting work called DIP, Deep Image Prior, proposed 2 years ago, as well as some other works. I think very recently, Carol also have a very nice paper along this line. But these works usually focus on image denoising. They are not really general, so that they can handle all the linear inverse problem. All right. So one which can be applied directly on solving the general linear inverse problem. One is DIP. The other one is Sure AMP, which is specifically designed for compressive sensing. Okay, we will compare this method in the experiment. So, 20 minutes introduction. So this is the background. Today I will introduce a self-supervised method to tackle the general image recovery problems. So of course, if you want to do a self-supervised learning for image recovery, you have to ask the question, without seeing any training examples, how a network can learn to predict the truth from a degraded observation. Okay, if you technically, the challenge is that how are you going to regularize the network to avoid the overfitting, right? For example, if you look at image denoising, so if suppose I only have one sample, we don't have any training sample, I have a Y to process. So suppose I just train a network directly to map Y to Y. Then the answer will be identity map. You just do nothing, right? If you do nothing, you get minimum cost, which will be 0. So this network is actually, if you can try, indeed, your network will converge to identity map. So the so-called deep image prior 2 years ago, actually, they have very interesting discovery. What they did is that they consider still chain such a cost function, which will lead to overfitting because it will converge to identity, right? However, they propose that when you train the network, the regular image structure will appear before random noise showing up. So which means you train the network during iterations when the iteration goes, more and more image regular structure will appear, but not those random patterns. After all the regular structure appear, the random noise will appear. Then the idea will be simple, just using so-called like early stopping. You stop train the network when the random noise will start to showing up. Okay, so they are using a UNet. Here I give you show you some examples, right? I just take some initial seed with random noise, Gaussian noise, right? Then I train the network using this trivial cost function, and after it go to 500 iterations, you can see you get the image, right? Just contain the noise, but after 3,000 iterations, you can see noise are gone. You are only left with image structure, right? However, you cannot continue. If you continue, the noise will be back. Okay, that's the so-called early stopping. You stop at 3,000 iterations. You get some good, not good, but okay denoising result. So you can see it's very simple to use. Just stop early, then you are done, right? You can use it to solve any general linear inverse problem. But the disadvantage is that the performance actually is not so impressive. It definitely worse than supervised learning method. Also, it cannot compete with the state-of-the-art non-learning method like the BM3D, the local method. Also, how to automatically stop is actually not trivial, okay? We say, okay, we stop before the noise is coming up, but how do we know noise is coming up? Of course, our human can do this visual inspection, but for the machine, it is difficult. So how to do it automatically is actually not trivial. All right, so we re-examine this problem, and we propose a work to do this self-supervised learning. And our work have 2 parts. The first is how to design a loss function. We're using the data augmentation, which is I have a single Y, I generate a set of image pairs. Based on a set of image pairs, I design a loss function. Okay. After that, you can see it actually statistics will approximate the supervised case. Okay, very interesting. The second one is that we consider to using neural network to approximate the minimum mean square error estimator by Bayesian inferences. Okay, I will talk about this more. In our case, our neural network is not just the network to learn the prior. It's more like a generator to generate the image. We have 2 parts. Part 1, how to design a loss function. So as I mentioned, is that this is what we will do. We will first augment the image to get a set of pairs. Then I define a loss function. Okay, its expectation of all the image pixels will actually equal to expectation of this one. So you can see here is only Y, right? But here you already see the truth, X. Okay, plus a constant, it doesn't matter. So as a result, you're gonna have a self-supervised loss function in such a form. This one, if you compare this with a supervised case where you have the truth, it's weaker because you still have A. But at least you get partially done. You introduce the truth. It's just the cost function defined in the range of A, not the full space yet. Okay, that's what we're going to achieve for the part 1. So the scheme for the data augmentation is you first randomly select a subset of image pixels and replacing their values. You're going to have 2 schemes. The first scheme is just replace it by 0. Okay. The second is replaced by the average of its neighboring pixels. That is, I take the pixel randomly, I replace this value by the average of its neighboring pixels. Okay, then it becomes a different image to the y. Then actually I can define such a replacing scheme using the Bernoulli random variables. Okay, I introduce a binary Bernoulli vector. You have certain probability to get 1 and 0 otherwise. Then this y tilde m can be defined as this. So this one is the pixels which are not selected. You keep as it is. These are the pixels which will be selected to replace, and you have some operations on that to replace it. That's a general mathematical formula, a definition for this y tilde. So once you have this y tilde, I introduce a loss function. That is, I will measure. Okay, this is the pixels which are smoothed away. Then I consider its prediction accuracy to the y, not x yet. But then you can prove. Suppose I consider IID random noise with 0 means. You can prove its expectation over all these instances actually is equal to this one. It's A of the prediction to the truth, which means it's you are predicting the truth in the range of A. So in the special case, when A is identity, this corresponding to image denoise. In this case, you actually said the expectation of this cost function is actually the same as the truth, same as a supervised case, right? You try to predict, but not predict y, but predict x from y tilde, not from y, but from y tilde. All right, so this is the self-supervised loss function we defined. You can see we actually, by using this data augmentation, we somehow get the partial of the supervised loss function, okay, just in the range. So what exactly this one is doing, I'm doing here is that here actually this is related to the image implanting. So I have image y, right? What I did, I just threw away certain pixels. Then this is what remained. So what I did is try to take this as input of the network to predict this one. That's how what this is about. Which means you are measuring the prediction error using the image which are not replaced to the image are replaced. So so now we have a weak form of the supervised loss function, right? And so you still have only partially solved the problem. That is, you still have the solution ambiguities. Secondly, in comparison to the supervised learning method, you only have one sample to train because you only have single x. You have different instance related to the x, but you have a single x. So you're going to have large variance. So we need additional techniques to get a better result. So we actually consider how to simulate approximation to the MME estimator using neural network with random process. So recall that MME estimator refers to the conditional expectation. Okay, as long as, which means you are somehow the average error over all x. So actually this one, if you compare with the most supervised learning method, MAP method, traditionally And MAP estimator, you can write this as this one, a very classic technique. This is the prior, that is the distribution of truth. Okay, so for instance, if you think about L1 norm based regularizations, you assume this P of X follows Laplacian distributions, then you're going to have L1 norm based regularization, right? But then the supervised learning actually can be thinking you are just somehow learn such a MAP estimator. But the problem happens is that we don't have the truth with me, right? I only have a Y. I mean, then I have no way to infer this P of X, not like supervised case. That's why we actually switch to approximate the MME estimators. So let's assume my network is a generative network for X. Then I can replace this posterior property by the posterior probability function regarding beta. Beta is the parameter of the neural network. So of course, no way you can handle it. Therefore, we just follow the we just follow the standard routine in Bayesian inference. I just approximate using some distribution I can calculate it. Of course, then the approximation accuracy will be depend on how well this I can approximate. So that means when I try to train the neural network, I try to minimize the Ki divergence. Okay, so once I have such a approximate MS estimator, I can have the prediction. Okay, this is you just take the average of all prediction to get the conditional expectation. So here we will examine two neural network with random process. One is so-called dropout network. Dropout network assume every this node follows a Bernoulli model, that is, it has certain probability to be dropped out. Then I have the result to minimize how to minimize its Ki divergence. I assume Gaussian white noise, then minimize this divergence. Indeed, is actually very simple. It just directly minimize this prediction in the range of A. And only difference that here you have random Bernoulli vector C, because I use this Bernoulli process to approximate, use it as a Q. Okay, another one is the Gaussian Bayes network, so which means every weight is not a fixed number. It's actually a random variable which draw from a normal distribution. Okay, then the idea is how I can minimize this Q, which means I try to find the parameter of these normal distributions. Then we also have the formula. It says if you want to assume, I still assume Gaussian white noise, then you want to minimize the Ki divergence. Essentially, you have this standard Fourier term, but you have additional regularizations on the mean and standard deviation of parameters of this normal distribution, as well as you have this term. Okay, so you have this. This is how you're gonna minimize the Ki divergence, because as you can see, both of these is actually you can using standard neural network to train it, because we actually derived what the cost function should be. Okay, then you just train the network to minimize the Ki divergence. You can do it in the standard neural network training procedures. Once you're done, then you just take T multiple neural networks from this, because now the network, the weight follows some random process, right? Then you just randomly draw different weights from this Bayesian network, you're going to have a multiple instances of neural network. Then you just take the average as the output. Okay. So I just want to recap what we did using this approximate MME estimator to do the self-supervised learning. The basic idea is that if you think about example learning, the existing supervised optimization unrolling is actually related to so-called boosting. And what we did is related to the bagging. The boosting means you have some input, you take model 1, model 2, model 3, and eventually go to the final prediction. You hope like every model will improve or will help to correct the error passed, the error of the estimator passed from the previous model. That's what boosting means. But here we're more or less using the bagging. That is, I generate multiple weak models. Okay, then hopefully they have some certain like independence, but their predictions are still related. Then I can put them together to get a better prediction. This is actually the bagging scheme in the example learning. Okay, so I want to rephrase what we have been done for the second part. As I mentioned that this supervised case is actually derived, try to simulate using neural network to learn an MAP estimator. But for our unsupervised learning, we actually try to simulate using network to simulate the MME estimator because we don't have choose to learn the P of X, the probability function of choose X. That's why we turn to MNC. So here I show you, I have maybe 10 minutes. Okay, I will do quick on the applications. So this, we first test the image denoising, okay? And we are using this dropout rate here. We have to mention this dropout rate is fixed as a parameter, and it actually will impact the performance. And then I do all these routine things as we mentioned. I just want to check to show you the result. If you compare our result on all the dataset-free method, our method is actually the best. It actually can beat the state-of-the-art non-learning method if you're checking. Okay. It also do better than DIP, and the DIP need to really careful to stop the iterations. Okay, but if we compare the supervised learning method, you can see our method is actually more or less, I would say, do things better on one data set, not as good as DNCNN in another data set. This DNCN is considered one of the state-of-the-art supervised denoising network. So you can see we actually provide competent performance to the supervised learning method. So we can also try this real data set, not real data, the real world noise, okay? And you can see our method is actually second best, and it's still slightly, I would say, actually, its performance is equal to the supervised method because its difference is 0.03. I mean, it's not significant. So here is one minor issue is that we have computational issues. So if you want to process 100 image, and you really need 24 hours, 1 day to finish it. So in comparison to the traditional regularization method like L1 regularizations, we actually, our approach now is like, I think 5 to 6 times slower than traditional regularization method. Okay, because we have to finish all the training and the test. Okay, this is show you the behavior of how because we are using the average from the multiple predictions. So you can see the prediction is quite consistent in terms of the performance. If I run in the average, it indeed increase one, and it will become saturated somehow after get to 20 20 averages, okay? And this is show you the stability of the training. It can be seen our method does not require any attention on how many iterations you want to go. As long as time allows, you go. You can see because the result will increase increase in the beginning and slower afterward. It's expected, and it's never going down. But if you look at DIP, you have to somehow stop in the middle. Otherwise, the performance will going down because the noise will showing up in the result. So second one, we also try this image deconvolution, okay? And of course, here I'm using the replacement using by local average, and I'm using dropout. Here I still use dropout. And here this is a setting of the data set. And you can see, if I check in our result to the dataset-free method, we actually are the best in most cases. It only is not as good as BM3D when the noise level is very low, 1%, and on the sound data set. So most time we provide the state-of-the-art performance. If you compare to the supervised method, well, it is, I would say it is actually somehow comparable. We don't have advantage, but we are comparable. So suppose let's, for instance, we compare this quite state-of-the-art supervised case. We actually are better in one case and better than him in one case, two case, three case, and worse than him in three case as well. So we actually somehow, I would say, not so much difference. If you look at the difference, it's not big as well. This is only 0.4. This is only 0.2. Okay, we provide competitive performance to the supervised learning solutions. And this is, again, you can see how the variations among different predictions will help to eventually give you a more accurate estimate. So last one, supervised. Okay. For the image compression, it's a very severely underdetermined linear system. Okay, it can be 10 times underdetermined. For if you have a CS sampling rate 10%. Okay, here I use a CNN with only decoder, no encoder. Why? Because we are using Gaussian random sensing matrix, so your input is random. There's no point to randomize again. Therefore, I only using random noise as input. I omit the data augmentation part. This is that, remember, when we're using the dropout process, we have to predefine the probability, the dropout rate. Here, if we switch to the Gaussian process, because we can automatically estimate the parameters without any manual or interaction. So this will be the cost function we're going to minimize. We're going to train, and here I want to show you result. So first you can see, of course, you say, well, you train a network, then you can use off-the-shelf regularization on the weights, right? So here I first show you if I don't use any regularization. This one is I use a traditional L2 norm square regularizations. You can see the performance is actually significantly worse than our approach. This implies that the off-the-shelf neural network regularization does not work for our task. So here I show you some comparison to, because there are many supervised, we only pick some of them. So for instance, this is total variation. This indeed is ADM net is quite famous supervised method for compressive sensing, and this is using the GAN. So, and this is DIP. We all compare. So you can see our result produce significant performance, significant advantage when you contain noise. It's quite interesting. If you think about, you have you can contain 10% of the noise. Our approach provides much better performance than any other supervised or unsupervised method or traditional method. Only when there is no noise, we are somehow, for some reason, we don't stand, but somehow not as good as DIP in one case, but still better in other masks. So as long as you have noisy measurement, our scheme actually provide the better performance than any existing supervised or unsupervised method. But our method is dataset free. You don't need any training sample. Okay, this is visual inspection. Okay, so in summary, we propose one is self-supervised loss function using data augmentation so that you can generate some like partial truth of the supervised loss function. And you can also, we propose using neural network to approximate MME estimator so as to get a very accurate result. So the performance, I will say, it's so far it's better than any other unsupervised or regularization method, but its performance is actually very competitive to the supervised solution. In future, we would like to invest two things. So far, we focus on the development of the software and algorithms. Now we want to sit back to check what exactly is behind to make it work well. Secondly, the speed is still concerned. It's 4 times slower than the traditional regularization method. So we want to develop more computationally efficient algorithm. Okay, these are the three young men I'm working on those. No, okay, three young people, young researchers I'm working with on this project, and well, we have two results are published in last year's conference, and actually we have published the code and the training examples. One is for denoising, one is for the conversation. You can check out the code and trained model. The other one is because a paper is still under review, so we'll publish it soon as long as it is get accepted. So that's all I want to say, and thank you all.
Thank you, Jihui. And now it's time for question and answer. So if you have any question, you can push the raise hand button, and then I will unmute you, and you can ask directly, or you can write it in the question and answer box, and then I will also unmute you, see whether you can ask first. Otherwise, I will read the question
okay,
out.
I can see one question from.
Oh, you can see her question. Good. Okay.
The audience. It says this approach is similar to the Sting unbiased estimators. I will say they are different. The Sting, sure, actually, I don't know whether I include the comparison in our slides, but you can check our paper. We include the comparison to the Sure in our papers. Actually, our performance is actually much better than Sure estimator. So the difference is that Sure actually try to using directly using regularization on the network weights, and ours you actually somehow using the random process to simulate multiple prediction. So then to average them out, this is actually give you advantage. And you can see actually this averaging brings out 1 to 2 dBs performance advantage. I think they are quite different in terms of the basic methodology and idea. We do have the comparison to the Sure.
Okay. Yeah. So we have another question from Rafael Orozco. So he say it looks like you are taking point-wise means for multiple evaluation of your network. Can you also take point-wise deviation statistics? Does this at all related to the uncertainty of the posterior?
Yes, I agree that more or less we actually the uncertainty of the posterior because we are using this Bayesian neural network, the uncertainty introduced by this indeed actually is useful. Yeah, but I'm not really familiar with you say take pointwise derivation statistics. yeah, you can somehow put this way.
Okay. So any other questions? I have a question. So your dropout rate, is it a robust? I mean, is the method robust against this parameter?
We actually, well, because for the neural network, we have two things. One is training. Actually, our method, we actually tried, because after we published paper, we tried our approach in different network architectures, including ResNet and UNet. The performance are similar. So in other words, the network architecture is not really a big concern. And regarding the training, we actually using the standard like training procedures. We don't introduce any particular techniques for the training. Then for the hyperparameter, if you use a Bernoulli process, then it is sensitive if you choose wrong the dropout rate. But this one, that's one of the reasons why we switch later to the Gaussian process, because that allow us to automatically estimate the parameters of the normal distributions. So there's no such high parameter involved if you're using Gaussian process. Yeah. But for the dropout, the dropout rate is quite important. For the other sensitivity, I don't know. We actually have quite extensive experiments for the denoising. We tried Gaussian, we tried Poisson, we tried the real world noise. They are all doing quite well. Yeah.
Okay.
And also for the computer sensing, we also tried Gaussian, tried Poisson, tried yeah. But I just show you some of the experiments.
Okay. So
Can I ask something, Raymond? Oh, yeah.
Yeah, sure. Go ahead.
Hui, so first of all, I really enjoyed your talk. Thank you very much. That was really, really interesting. Also super well explained. Thank you. Hui, what can you say about how well you are actually approximating the MMSE?
We don't know.
Yeah.
I just say, because I have a network that's very complicated, then I just say every weight is a Gaussian process, then I have such a very complex function, right? But how well it indeed approximate the probability distribution I really want, I don't know. I just hope it's good. It's good enough.
But, I mean, the results are definitely encouraging. Yeah.
Yeah, right. But we don't have any result or any mathematical analysis on how really this, because network is very complicated. Then you put all the Gaussian process together. Actually, it's very hard to analyze. It's what is a function, but it's indeed a very interesting math question. Yeah.
Yeah. Maybe you could. Maybe one could try with a super simple version of what you're doing.
Yes.
I don't know, but yes. So
yes. Thank you. Yeah.
Really interesting. Thank you, Hui.
Yes, that's a great point. Yeah, that we should because I think we don't have. I have to admit, we just develop algorithms and I try to see how well it works well in the practice. But right now we don't any. We just started to think about what is math behind it.
Yeah. Thank you.
Okay.
Thank you.
Any other questions? Let me see. Okay, so there seems to be no other questions. So if not, then maybe we will finish now. And thanks, Fei, for this very interesting and exciting talk. And so the Chinese New Year is coming up in 2 days. I want to take this opportunity to wish everyone a very happy and healthy year of the ox. See you next Wednesday.
Thank you, Raymond.
Thank you for.
Thanks, Raymond.